So in the previous video, I asked you to think about this problem, whether comparing 3% and 24% defined by these probabilities, defined by these events, make any case for discrimination. I think the answer is no. It does not mean there is no discrimination, but these numbers are not a fair comparison. That's what I'm saying here. The reason is, let's think about how the probabilities are defined. The underlying experiment is that there are 1,200 police officers who are candidates for a promotion. So there are 1,200 officers, and we randomly choose one of them. And we are calculating the probability that the randomly chosen candidate is female and promoted or male and promoted. So just put everyone here and choose one, and let's see if this guy, whether this guy is promoted or not, or whether this guy is female or not. The reason why I think it's unfair comparison is because the candidate pool size is totally different for male and female. So as you have seen before, there are only this many females compared to men. So it is the pool sizes are so much different. So when you randomly choose one candidate out of everyone, then it is more likely to see a male candidate regardless of promotion. So even without having promotion, regardless of the promotion variable, the probability associated with male must be much larger than the same probability for female, right? That is the difference in pool sizes. There are much more male police officers than female police officers. So automatically after promotion, there may be much more male officers just because there were larger pool, even there was no discrimination. So the comparison itself is not fair. They cannot be compared one-to-one. How can we fix this problem? The probability we have to define is this. So if I was female, if a candidate was female, what is the probability of promotion? If a candidate was female, what is the probability that she is promoted? And compare that with what if the candidate was male, and then what is the probability that he is promoted? So change the condition and think about the probability of promotion for female and probability of promotion for male. This is one-to-one comparison. So in our numbers, using our numbers, you can see what I'm saying here is there are 240 female candidates. So if you randomly choose one of them, you choose only among the female candidates, not from everyone. Or if you randomly choose one person, one female candidate, then only 36 were promoted, which is 36 out of 240 is 15%. And on the other hand, if you do the same thing for men, there are 960 male candidates, and among them, if you choose one candidate randomly from this man, then 288 are promoted. So the probability of promotion is 288 out of 960, which is 30%. So this is, intuitively speaking, I think it's very much straightforward. This means much more than the previous numbers. Now you can claim that something is not going well, or the still, now it is a fair comparison, but the numbers are different too much. So now we are going to formulate this framework. Why our original, the former probabilities were misleading, and why these probabilities are doing well. So we need to define this. The latter probabilities or conditional probabilities. And to define conditional probability, we have to think about two events. Two events now. For events A and B, the conditional probability of A given B is defined as the probability that A happens under the assumption, under the condition that B has already happened. B is the condition, and we know that it happened. It's assumed to be always happen. So I don't care how likely it is. B may not happen. Like I don't know. B may be a rare event, but I don't care. I assume that it happened. And then what is the probability of A happens? And notation is using bar. Probability of A given B. I usually read it as probability of A given B. So then it's natural. And this vertical bar is called bar. Mathematical symbol is called bar. And here, clearly the event A and B play different roles in this definition. So I'm going to call A as the event of interest. So A is the main event we are interested in, and B is called the conditioning event. It is just a condition. I don't know how likely it is, it just happened, right? So given that B already happened, what is the probability of A? So randomness is only in A, right? So randomness in B does not matter at all. Back to our example. How can you calculate that? So now this conditional probability of P, promotion, given M, man. Now, so we among man, I know that candidate is already a man, and what is the probability of promotion? So being a man is not a random event; it's given. And the simple idea to calculate this conditional probability is to erase the observations do not satisfy the condition. So in this 2x2 table, only these two, the first column satisfies the condition. As I said, the condition is man. So only the first column, on the observations in the first column satisfy the condition. So what I suggest here is erase the others. The female observations are not relevant to what we are calculating. So we are calculating a probability conditional on man. So female observations are of no use. They are useless, erased, when you calculate conditional on M. And then it is clear. It is simply like now M is fixed, so then it is either promoted or not. And it's very easy to calculate what's going on. So probability of promotion is this, that is probability of P given M, right? Again, the idea is deleting the observations that do not satisfy the condition. Very intuitive, right? And try the same thing. Now we would like to calculate the conditional probability of promotion given that we know that the candidate is female. So we know that the candidate is female. Then given that situation, what is the conditional probability of promotion? Try this by yourself, and I'm going to stop this video here. Please and play the next video after you calculate this. Please answer this question and then check if you're correct in the next video. Thank you for watching.